What you are watching right now is a fully optimized Parkour TAS. By the end of this video, you will know exactly how to create one yourself. Before we start, I want to give a short introduction to TASing in general and show what makes Parkour TASing its own discipline in Minecraft. After that, I will give a quick refresher on Minecraft's movement mechanics. This is not strictly needed, but helps tremendously when creating TASs. After that, we'll create a TAS manually and then use the angle solver to optimize it. We will be able to see that we can save over an entire second on this short course. So what exactly is a TAS? TAS stands for Tool Assisted Speedrun, and essentially it is just a fixed sequence of inputs. For every single frame of the game, it defines which buttons are held and where you're looking. Feed that sequence back into the game and your run executes exactly as written. The tool assisted part describes how the run is created and not how it's played back. While making a TAS, you can, for example, slow down the game, pause it, step forward one frame, create save states, and rewind whatever position you want to if you make a mistake. You're also able to read the game's internal values, like for example your exact position or speed, instead of having to eyeball it. But all of that only exists during creation. On playback, the game isn't modified at all, and it just simply executes your input sequence that you predefined. What makes Minecraft Parkour TASing different to normal Minecraft TASing? Minecraft runs its game logic at 20 ticks per second, so instead of frames, we think in ticks. Every tick the game reads your held keys and your look direction, runs its movement formulas, updates collisions, and moves your player. A Parkour TAS is exactly that list. Your W, A, S, D keys, jumping, sneaking, sprinting, and your yaw value. In newer versions, the pitch is important as well. And that's really all it is, because Parkour only cares about the movement. We don't want to manipulate RNG, we don't interact with the world apart from placing and breaking blocks, trapdoors or buttons, and we don't touch entities at all, because entities are non-deterministic. The same inputs wouldn't reliably give you the same result. Pure movement, on the other hand, is fully deterministic. If you have the same starting position with the same inputs, you will always get the same outcome. And the Parkour calculator does this to bite exactness. If you want to test Minecraft as a whole, with full speedruns and RNG manipulation and everything, you can check out LoTAS or the TAS mod by Scribble, links in the description. But to write good Parkour or movement TASes, you first need to understand some fundamentals of the game's movement mechanics. So let's quickly go over how Minecraft movement actually works. Minecraft movement appears to be very smooth and continuous, but in reality it's not. The game updates in steps, and those steps are called ticks. You get 20 of them per second, so one tick every 0.05 seconds. And the player really only exists at these positions. And in between two ticks, the player just doesn't exist. The game never calculates anything there. Inside each tick, the game does the same three things. It reads your inputs, moves you vertically, and then moves you horizontally. Because of this, some movement things in Minecraft may be unintuitive at first. Let's consider jumping. So we are sprinting toward an edge, and every tick looks the same. The game tries to pull us down, the block below says no, so on ground stays true. Then we slide forward a bit. Tick 5 is where it gets interesting. When the tick starts, the hitbox is still above the block, so the vertical move finds ground like always. But then the horizontal move pushes us fully past the edge, and after that move, nothing rechecks the on-ground state. Tick 6, we press space, the game checks on ground, and that flag was written during the last vertical move, back when we are still above the block. It still says true, so we get our jump a full tick after leaving the edge. Now the same run, but we press space one tick later. This time, tick 6 has no space input, so the vertical move runs, finds nothing underneath, makes the player fall, and flips on ground to false. And when space arrives on tick 7, the check reads false, nothing happens, and we just fall. So the important thing here is to remember that the tick before you press jump has to be above a block and on the ground, not the jump tick itself. The jump tick itself can even happen mid-air, as we just saw. And landing works exactly by the same rules. So let's take a look at landing ticks. Here is a regular sprint jump. Look at where the landing tick starts. The hitbox is already over the block. So when the vertical move sweeps down, there's a surface underneath it and we land. After that, the horizontal move just slides us along the top. Now the exact same jump, just starting a quarter block further back. This time the landing tick starts with nothing but air under the hitbox. The vertical move has nothing to land on, so it drops us below the surface. And now the horizontal move drives us straight into the wall. All our horizontal movement is gone and the sprint resets. So to land, you already have to be above the block one tick before landing itself. Alright, vertical before horizontal explains jumping and landing, but the horizontal move itself hides one more order. The horizontal move is actually two separate moves. Split everything into X's and you get move Y, move X and move Z. Y we've already covered, and X always runs before Z. This is a Z-facing jump. We pass the wall on the Z-axis and we need a bit of X movement to get around its face. Move X runs first, so by the time move Z pushes us past the wall, the hitbox is already clear of its face, and we get through. Now the X-facing mirrored case. We want to pass the wall on the X-axis. Move X runs first again. This time X is the axis that goes past the wall, and the hitbox is still in front of its face. So we run straight into it. Move Z would have pushed us clear, but it runs after X, which is one move too late. So on X facing, you already have to be clear of the wall's face from the tick before. Then move X has nothing in front of it, and we get past. That is the rule. On X-facing jumps, clear the wall one tick before you pass it. On 1.14 and newer versions, the order isn't fixed anymore, and it depends on your velocity. Here, the faster axis behaves like the X-axis. And that's all the fundamental movement theory we need. Time to actually build a TAS. Let's start creating a TAS. First of all, check what keybinds your Parkour calculator has set. For me, opening the UI is button 5 on my mouse. So open your Parkour calculator, click on File, click on New TAS and enter a name. Click on Save. Now right click and set to user position. Now the TAS is exactly where you are and faces where you face. We want to start right from the middle block, and to configure this more precisely, we have our chords 0.5, 18.5 and 64. We go onto the first tick, which is the start tick, expand it, and here we can edit where we start from. So let's make this more precise. Let's get the yaw facing to exactly 0 and have the pitch 55. Now let's add a couple ticks. And I think we need like 200 ticks, and we add them to row's end. And now we have those ticks. If you now click on one entry and hold the mouse button and scroll down, you can just add a lot of W presses, and we do the same with the sprinting. And now the TAS already sprints straight in one direction. As you see, the TAS has, or the path has different colorings. A selected tick is dark blue. The ground ticks are white. Collision ticks are red. Sneak ticks are orange and air ticks are light blue. All these values can be customized under settings and preferences, render colors. The TAS does not react on dynamic block changes. So in this case, it seems like the TAS would walk straight through, and to update it, select a tick before and update this tick by hand. For example, pressing and releasing W again. It is important to understand that the TAS uses a sort of checkpoint system. So if I change tick 12, all the prior ticks are not resimulated. So for example, let's replace this again. I place a block and I update a tick, for example here. The collision that occurs here is not resolved. If you want to replay a TAS, you would press the key P and it replays. To stop the replay, press P again, and on servers you get teleported exactly where you started. On single player, you end where the TAS ends. If you select a tick and press P to play the TAS, it starts from that selected tick. To unselect it, you can press L or whatever you have configured in your settings. As you saw, you can select a tick, and this selected tick shows some tick information in this little window. There are multiple things you could do. For example, if you want to always see that tick info window, you can go into settings, general, and click on tick info. And that allows you to always see that tick info window, and you can just click on ticks and see what they are currently doing. There are also additional settings for that tick info. If you go in here, you can customize whatever you want to see. For example, if you want to see the speed. If you don't want to see this tick info window at all, you can also disable it right here on the tick info, and now it will never show up again. First, we will create the TAS for this map with our own hands, and after that we will use the angle solver to optimize the TAS. So let's start jumping. And the first thing you will notice is, okay, I don't want to hand edit the yaws. And what you can do is right click on a tick and rotate it. Besides rotating the yaw, you are also able to rotate the pitch by holding Control, and this pitch gizmo shows. There are a couple settings to make this visualizing easier. First of all, you can enable in the input table the pitch column, but you're also able to set these two checkboxes. And now whatever tick you select, you're seeing its pitch and hit distance or hit line as a line right here. Furthermore, you can also change the arrow type to combine pitch and yaw. And now you're seeing, okay, here it's facing down. Now I can make it facing up or any other angle. So let's continue.
Let's jump here, click on here, do a jump here over to the stair. Let's get some run ticks. Let's jump here. Nice, okay. On to the slime. Okay, we are still under the block. No, we're not under the block anymore. And you will notice this button there, that this button has a reason, because I also want to show that you can interact with things inside your TAS replay, so you can click buttons. Sadly, buttons don't do anything on HPK. I wanted to have a piston layout here, but yeah, sadly, it does not work, so just pretend there's something going on with this button and this needs to be pressed. Alright, so we're almost there. Now coming to the squeeze. And all the obstacles in here have some sort of reasoning. I've added them. We will see that once we use the angle solver later. Now an X facing W. Not too bad. Okay, no, we need to a couple more run ticks here. And final jump. We don't have enough ticks. Let's duplicate a couple. You can select them and duplicate them. That's how I like to add new ticks, because then they are already
pressing W and sprinting. Now we're in the goal, and probably tick 202 or 203 is what is reaching this goal. Now let's take a look and replay the TAS. Yeah, we can pretty much see it's we are very fast in creating these, but we are also not optimal at all. Like, we have so many run ticks here and there. Don't forget to save. Usually, or the default setting has autosave enabled, but I don't like that because sometimes I do a mistake early and then it autosaves and I've pretty much lost a lot of progress. So I would highly suggest disabling autosave, and a quick way to save is Control S. That saves it. That's what I do. All right, now we come to the angle solver part, or the part that's a bit more daunting, but it is very, very powerful. So I would highly recommend sticking around. First of all, let's duplicate the save. So HPK TAS, and now we call a duplicate save angle solver. And I will immediately go ahead and throw out everything up until tick 39. So first of all, you will need to enable the angle solver under view. Click here. Now you got the angle solver here. Let's optimize this first part, because this is quite easy. We don't have any collisions. The first thing you need to understand is the solver, that when you click on solve, is a mathematical model and has nothing to do with the ticks you see simulated here. The ticks you see simulated are simulated or run through a simulation entity, which mimics exactly how the player would move. And the solver is just a mathematical model. The simulation entity, the path you see here, knows about collisions, knows about pretty much anything and everything that goes on in the world. The mathematical model behind the solver does not. The mathematical solver does not know that it is colliding on the ground here, or that it is running into a block. And this is what you have to tell the angle solver by setting constraints and states. So the first thing you will always need to do is tell it when the angle solver is on ground. And we can already see that each tick that is spent on ground is highlighted gray. And when the angle solver is enabled, you are able to expand each tick, and it shows a couple more settings, but don't worry. The only thing we want to set is the slipperiness on default, which is ground state. So now I have set the slipperiness on default, and if I hold the Alt key and drag down the slipperiness, I duplicate it. And what we want to do is set the slipperiness value on each ground tick. Let's do that real quick. All right. Now we need to tell the solver from where to where it should solve. And in this case, we want to solve from tick 1 to tick 39. So the start tick is tick 1, the end tick is, or the goal tick is tick 39. And finally, we need to tell it what it should solve for. In this case, it should solve for the negative X direction. So X in this direction goes down, so we want to minimize X. Also make sure that you select the effort fast. Fast is, for most cases, enough. What fast does is it stops on the first feasible solution it finds. Optimize goes a bit further. It has a time budget and it spends the time budget and tries to optimize the path, but fast is already very good. Okay, now we have this. So if I click on solve now, what will happen? Solving will do exactly what we told it to. It should try to minimize into the X direction. And since it does not know about all these blocks, it will just go into that direction. And the solver does also notice that something went wrong. We see that the solve diverged at tick 12. And this is exactly one tick after the solver thought it would land and be on the ground. So if you see that the sim diverged, it is very often the case that you misconfigured something somewhere. And it means that the mathematical model diverged from the simulation entity it tried to predict. When this happens, always ensure that the ground state is set correctly and that the solve does not collide anywhere. Also ensure that if you have any ticks that are not spent sprinting, you don't set sprint to always, but to derive. And as you see, it will 45 strafe into this direction. So we told it about the slipperiness or those places where it's on the ground, and we see that it respects that. So the first turn is directly on 135, strafe, face straight, strafe again, and so on. So it does those 45 strafes perfectly into the direction, but it does not respect that there are blocks. And we need to tell it that now. So let's move the path back into shape. But yeah, I think this works for now. Or now you would use a lot of the B key. So you now need to tell it that it has to land on this block. And what tick must be above this block for it to land? That's the landing tick. This is one tick before the player is on ground state again. So this tick must be above this block in order for the player to land on this block. So hovering over this top of the block and pressing B adds a constraint or an area of where the player must be. And there are, again, a couple settings. And the constraints, you can disable constraints, but I would not recommend that. And you can expand the constraint by the player hitbox. What we are seeing now is that this tick and its green outline must be encompassed by this constraint. The green outline is the exact hitbox of the player. And some people like to use this. I think it is too much clutter and I very rarely use that. There's also a 3D version of this. I usually don't use that. So this tick must be on the block and this tick must be on the block because this tick is the jump tick and one tick before we jump, we must still be on the block. The same holds true here. Since this is the tick that lands and the tick before it jumps, only this tick needs to be on the block. And then we also want to have, I think, this tick, yes, 66.01 on top of the stair. And we see this shape now differs from the block shape because the collision, if you use the B hotkey, the constraint knows about the block's footprint and expands it by that. Okay, and this is already all we need. And if we click on solve now, we see it does solve correctly and we see this is optimized into that direction, minimizing X. This is exactly at or almost exactly at this block's corner. We have used fast and not optimize. I think if I would use optimize, it would go a little further. Yes, now X is exactly at dot 3, traded in for this axis. So let's replay this real quick. Too bad, not too bad, but we waste a lot of ticks and we can see that. We waste some ticks here. We are not going straight anymore. We are curving a little. We are curving here. Usually means we are wasting time. The strong part about this is I can just go in, select a tick, right click and delete this tick and now click on solve again. And it solves it again. And I can do that again and solve it again and do that again and solve it again. And each time I shave off one tick and it's as optimal as it was before. Now we can go in here and remove 2 ticks here and still solve. And now we have pretty much optimized it. If I would remove this tick, for example, I would not make it onto this block anymore. So this tick is mandatory, solving it again. Okay, let's look at this. What did we find? All right, looks nice. The only thing that's quite annoying are the 45 strafes that are forced. And for that, we can change the default state of this TAS. We can say to keep the inputs. So let's keep the inputs and remove all the A presses. What it is now trying to do is it tries to find the yaw values with the inputs given and not force a 45 anymore. So if I solve it now and let's take a look at it, this looks a lot cleaner already. And you could also play around a lot with this, like alternating the A presses. I think this is quite funny, or adding some D presses in there as well. Yeah, let's see what this looks like if I solve this now. And let's play it. Yeah, I think this is a way of playing as well. You can see it just goes zigzag here because it tries to optimize, of course. So now you still might wonder why is sprint, what is this thing doing? And this is not used right now, but it is still very important. So I want to give it a little explanation at least. I have already told you that the mathematical model behind this does not know about its state. Right now, it assumes every single tick is a sprint tick. But for example, what happens if I want to have one tick, for example, where nothing happens? Now, this simulation desyncs because it still thinks the player is sprinting here, but it is pressing nothing. And to be able to know what state it is in at this tick, there is a setting for driving the sprint. And now the mathematical model just takes what the simulation entity knows about its sprint state. So if I solve it from here, now it would work again because the sprint state is sampled from that simulation entity. The reason why this is not a default value is that if this path collides somewhere when solving, because we have forgotten, for example, some constraints somewhere, then every single tick after that would lose its sprint state And the solver would work with that lost sprint state. So it would assume there's no sprint state again. So solving twice would result in 2 different outcomes. And that is very confusing for the player. So that is why the default state is to always assume sprinting. So if you want to do something with sneak ticks or where you have W released for a couple ticks, ensure that you have inputs keep. Otherwise it would just fill them up with 45 strafes again and sprinting derive. All right, but let's continue. We have this trapdoor here. A 3BC here is maybe possible. So how do we enforce that now? So we see that those two ticks collide because they're already too high. What this tells us is that this tick must be under the ceiling, so these 2 ticks bump below the ceiling and we gain 2 ticks. And how do we do that? Well, we just select this tick and say, all right, be within this constraint. So be within this trapdoor's hitbox. Now we also need to shift the go tick and solve. And something we did wrong now is we have marked these additional ticks here as ground ticks. They are not on the ground. So we need to remove them and resolve. And now we can see it's optimized the path below this trapdoor. Let's take a look at it. And yeah, that looks like a 3BC. Now let's see, can we jump from this tick already? This jump tick must be out of this trapdoor's hitbox again. So we add a constraint onto this side, and this is a keep out constraint. So this essentially tells the solver that this tick must be in front of the trapdoor. And don't forget, we are talking about the player's hitbox. So this green square must be behind this purple wall. So let's solve and see. Right, I of course have to move this and add the slipperiness. We are actually able to do that. So this tick is now below this trapdoor and this tick is behind this trapdoor and we are able to jump. Now we still need to make it onto the slime and the slime looks very far away. This is the landing tick and this tick needs to be within the slime's hitbox. But let's see if we can make it. For this, we can hold Control and click B and now it select the hitbox of the slime, not the hitbox of the block. And this tick must be on the slime. This tick is the landing tick, but this tick is the bounce tick, which must be over the slime. So let's see if this is possible. So let's move it to here. And here we would also need to set the slime slipperiness. Slime has a different slipperiness than ground. This must be slime slipperiness now. Let's see, solve. And we can see it does not work. Maybe it works with 45 strafing. And yes, it does. So in this case, 45 strafing actually makes a difference because this is quite a tight jump. So let's continue. And after that, we will take care of this button. And I show you how to angle solve with this button in mind as well. This tick now needs to land on the block. And let's expand the solve again and click on solve. This still makes it as well. So let me replay and you can select the range by holding shift and clicking. So let me replay this. This is how it looks like now. Okay, so before we solve for the button, let's do one more optimization because I don't like that it's just 45 spamming everywhere. What we can do now is go on keep and derive and just start removing strafe keys. So let's see what strafe keys are actually required or what 45 strafes are actually required. It seems like that this 45 strafe here is required because it stopped solving. Let's see if we need to 45 strafe all the slime. Yes, all the slime is also 45, most likely at least. So let's take a look now. All right, does not look too bad. So how do we integrate now the button right here? And for this, there are a couple things we can do. First of all, we need to enable some settings. We want to modify the pitch. And here we can set a couple more visible columns for the input table. We want to see the pitch and we want to have the right button click. So those are what we want to see. And we want to see hit distance lines of the tick. I mean, this is now barely visible. Okay, now it's a little bit more visible, but here we see what the entity actually looks at. This is the hit range of the entity. And if we hold Control now and right click on the tick, we can change the pitch of the entity. So now it is facing there. Now we just need to rotate it a little and a little upwards. And we can see as soon as it interacts with something, it highlights green. And in this case, we see now, okay, we are hitting this button. Now we can take a look in here and we are seeing, okay, it is hitting that button. And what I like to do is, so we see here now we are at -23, pitch -23. I like to make an absolute value with this. And we can do that by pressing F and then entering that number. If you press F inside a pitch or yaw value, it takes the absolute value and it will not change that. So for example, if I say this must always phase to, let's say, 45. Now it phases always to 45. And if I change this here, you will see that this is always an absolute value phasing to 45 now. This is how you could, for example, log a specific trajectory from getting modified if you change later ticks. But yeah, let's remove that again. So now the question becomes, how do we force this tick to continue phasing there while angle solving? And for this, we can expand this tick, go to add constraint, select the phasing constraint, and now just tell it to equal, in this case, 43. Now setting 43 here, and now solving again. And as you see, this tick right here, those entries are relative values from the prior tick, but this tick right here now almost exactly phases to 43. So we solved it, it is angle solved, but this is still exactly pinned on this button. Okay, what we have forgotten is to add the right mouse button click. You need to trust me on this. Replaying it will not show me clicking the button because the replay is on a ghost entity and the ghost entity does not interact with buttons on servers, but it would work on single player. Replaying would look like this. Sadly, it looks like I don't hit the button, but this is just the replay lagging a little bit behind visually, but the physics would hit this button. So you need to trust me on that. The button is being pressed here. For this, I already know we want to jump as late as possible. I have already tested this in a prior test. Jumping as early as possible will waste 2 ticks. Jumping as late as possible is 2 ticks fast. But what we still want to do is optimize into that direction. And this direction is positive X. So we want to maximize X, but we also want to get, I believe, this tick into the ladder hitbox. And for that, we can hold Control again and press B. And now we selected the ladder's hitbox. And now we need to add a lot of default slipperiness values right here, right? And we want to solve up until tick 84. Okay, and here we go. Let me see if this is correct. This does not seem correct. So we might need a 45 strafe for this as well, just to be a little bit faster. Now let's align it. And this is still not fast enough. So let's add a couple more 45 ticks. And now we run into one issue because this tick is 1 tick before jumping and it is not on the block. So we just add a constraint here. All right. I think this is now enough. Yes. And here we see this tick, which I wanted on the ladder already, being on the ladder, because now we can do a little ladder trick right here, right? This .2837 allows us to release W1 tick here. And now watch what happens with these ticks. Those are the ground ticks. They shift by 2. So we are already landing by tick 93 instead of 95. And this is exactly what I try to get at. Another interesting part will be the squeeze right here, how we angle solve the squeeze. Jumping from here does not make it, but we are very close. So this tick must be on the block. This tick is colliding and the difference between these two is very close. So a 45 strafe might be a way to do this. Also, one note on this ladder, we can't solve or angle solve ladders as of now because they collide with the wall and we can't represent collisions. Ladders are usually, you need to cut off the angle solve here. So in this case, the angle solve would continue from tick 93. So tick 93 is the new start tick. Need a couple slipperiness ticks here. And now move the go tick here. Let's see if it's possible without a 45. No, it's not by 0.02. Let's see what 45 does. And a 45 would land it. How much do we land it by? By 0.01. Okay, so this 45 is required. Let's switch back. We don't want to spam 45s. And now we need to somehow get in here. Also on tick jump. Let's eyeball this. This looks good. And now what we would need to do is, first of all, I would check, is this colliding? Yes, this would collide if it would not already be past this corner. That is good to know. I would add one here, one here. So those are, once again, the constraints to keep out of those 2 walls. And now we would just add one here and one here, one here and one here. And apparently here we are also still colliding. Let's try with this first. One here, and this must be landing there. We are going into this direction. This is negative Z, so we want to minimize Z. Now we want to add the slipperiness values again. Never forget those, otherwise your task will not, or the solver will not solve it correctly. And click on solve again. Okay, what is going on here now? We are turning in way too early and these are just colliding. One thing we could do is try to force them to avoid this already here. And yeah, nice. Wow, this went quite quickly. Now this is literally only sprint because we are not touching any walls. We don't get any collision here. I want to see what this looks like actually. Nice. But now we also need enough momentum to 1 tick this double neos. With this, we don't even land here. So let's get this to landing there first. and solve. And now we are colliding again. For this, I will move it one tick back again and solve it, because now we can see which ticks are already able to pass if you full momentum in here. And these ticks are passing. So what I would also say is this tick must be past this cobble wall. And now move it one tick down again. I'm not sure. Can this tick be one in front of the wall? Okay, now we are over jumping this block. So add a constraint here. This should be avoiding the wall there. And now we have quite a mess here, but yeah, it does work. And now let's see if we can one tick this. This looks not very promising so far. This is an X-facing Neo. In this case, it is good because we only get this tick past this wall. We could, if this tick now collides, we could add a constraint like this. If it would be X-facing, this tick would need to have these two constraints because it must be past this wall and not collided into this wall, but it's only Z-facing, so we only need this, or if this collides, this constraint here. So let's see if this works. Can we one tick this? Solve. And yes, we can one tick it. And interestingly, we have a couple collisions here which desync the solve. It still found a solution. So let me add a couple more constraints here. Nice. Okay. We only sprinted it again. This lands now here. And we want to maximize X. Right now it tries to go in this direction, so it cuts very short, or it cuts it very short. But we see, wow, we make it by quite a huge margin. So this tick already makes, and we don't even need this probably. Oh, wow. It just switched sides. Okay, that's crazy. No, I guess we do need this side. I have never seen this. Honestly, I've never seen this. The rest is probably just possible by hand. And so probably this tick, or maybe this tick, would now make it into the goal, and we did it with 176 ticks compared to the 200 something, a lot better. And now let's take a look at the TAS. And see, it's not very difficult. You need to get a bit used to it, but then it's just thinking about where we can add constraints. So yeah, if you have any questions, feel free to reach out to me on Discord or to Yindranth or Draku. Those are also very knowledgeable.